0.9 times 70 divided by 2.5.
Oh, you don't times it, you subtract it.
Let's take a look at what we've got here. Okay, so starting off for part A, we are given that we are looking for the area between the z-scores that we were trying to find. We want that to account for 95% of the total area under the curve. What do we do in order to take an area and convert it into z-scores? What calculator function are we going to use? Inverse norm. So inverse norm, which is that third calculator option. If we're looking for 95% of the area, what should we use for area? 0.95. Very good. In this case, since we're looking for z-scores, what would we use for mu and for sigma? 0 and 1. And then if we're looking for the area to be between two z-score, I guess it doesn't say between two here, but if we're looking for multiple z-scores between which we see this area, we should be center. Very good. And so what are these z-scores that we get here? Six and 1.96. Very good. Okay. So for B, we have a couple of different options here. One, and the one that we are going to kind of be focusing on today, at least for the first bit, would be to take this z-score that we have gotten and convert it into an x value. That's not too horrible to do. What's our formula that we could use that lets us go back and forth between x value and z-score? Yeah, what's our z-score formula? Other way there. Yeah, x minus mean. Yeah. Over the standard deviation. Very, very good. In this case, we have two z-scores that we need to convert. And so we'll run this formula both. We could also take this formula and convert it to make it a little bit more usable for x. So kind of do some packaging on it, some pre-processing beforehand. You should get that x is equal to mu plus z times sigma, which is just to say we take the mean and then we are going to add, well, this z times sigma, remember here, this is like almost like the distance above or below the mean, depending on whether z is positive or negative. And so adding that distance to the mean gives us exactly where that x value should be. So in this case, either way is fine. You can set up and solve for x. That's totally fine. You can use the solved version. Either way is great. I get that x should be equal to, in this case, 70 plus, we said, negative 1.96 times that 2.5. And then our other x should be 70 plus positive 1.96 times that 2.5. What are the values that we get here for x? 74.1 and going to be the same distance, but below rather than above. So this was really for how I have this written, I'd probably reverse the order. So this would be the lower the lower x value, 65.9 and 74.1. 70, this was 2. Sorry, reversed. This is reversed. 65.1 and 74.9. Well, reversed. Okay, so that's totally fine. That's, do we have a question? Or is that not related? Sorry, you're good. So this is great. This totally works. This would be the algebraic way to go about it. What could I have done to get my non-standardized values though, right from the start? Like if we just treated this as one question and the question was find this, and I didn't want to go through converting these z-scores into x values, what could I have entered instead? Yeah, Abby. Yeah. Yeah, so inverse norm again. Okay, so this is inverse norm. We are inputting same area, right? 95%. But now what is our non-standardized mu going to be? What is our non-standardized sigma? And in this case, we still want center. And if you enter this, you get the exact same thing that we got above. Which is totally fine. Either way works great. Solving it isn't exactly necessarily all that challenging, but we can also let our calculator do that part of the work for us as well. If we felt good about the spell work, then we should be in a really, really good spot for 6-1. This is like basically all we are going to do in 6-1. We have essentially accomplished 6-1 with we've got a slight twist that we'll need to make on this. But with that in mind, do we have any questions from the bell work? Anything that we would like to address? Anything that we don't understand? Yeah. I think there are technically 7. I think we're only going to get through like 3 of them. Yeah, we're going to start review as well. Any other questions? Hopefully fairly reminiscent of what we were doing in Unit 5. Not too much of a stretch from that. Okay, yeah, this is essentially confidence intervals, what we have just constructed. A little bit of an adjustment that we'll need to see before what we're working with are actually the confidence intervals that we're going to be talking about. But this is essentially the gist. The idea that if I want to talk about what's going on in between 2 different x values, if I want to find 2 different x values that represent kind of the boundary between which we see like 95 or 99 or 90 or 80% of our data, then we can construct the z-scores for it. And we can convert those z-scores into x values without all that much trouble. Now, what we are going to be doing is not quite this. The main difference between what we're going to do and what we just did for the bell work is that rather than starting with the population, we're going to be starting with instead a sample and be trying to use the sample to make some kind of claim about the population. Now, algebraically, there is a point of adjustment that we are going to make in order to account for the fact that what we are talking about is in fact a sample rather than the true population, but that's something that we dealt with in 5.7. So again, should not be particularly crazy, should not be all that bad. All right. So let's just start with the very idea of what do we gain when we are talking about an interval of values rather than just like a particular value. So I want to take a look at this first kind of mini example here. Or in this case, we are looking at we're looking to try and estimate the average age of students in a high school. And to this end, the person who's interested in this randomly selects 50 students and takes the mean of this sample. The mean turns out to be 16.3 years. So the mean, not of the population, because that's what we're trying to figure out, but of the sample is 16.3. Now, given that the mean of this sample is 16.3, what would be our best guess as to what the population mean should be from the information that we have? 16.3, right? We expect X bar and mu to work out to be about the same. So our best guess from this is that the true mean, mu, should be equal to 16.3. Now, that being said, that's our best guess. If we had to pick a number that we expected the mean to be, this would be that number. How likely is it that this is actually correct? If we're taking a sample of, let's say, like 50 out of 3,000, we'll use Collierville schools as kind of our example here. How likely is it that our one sample matches up perfectly with the actual true population mean? Not super likely. Yeah, unless we're being very, very choosy, unless we do a really good job of being super representative, we're not really necessarily going to expect this to be spot on perfect. It's our best guess, but we shouldn't necessarily be that confident that this guess is perfectly correct, right? And in fact, we wouldn't expect it to be perfectly correct, right? We would expect to see a slight amount of difference between the sample and the true population. Now, this 16.3 is what is called a point estimate. And thinking about this as being kind of like the best guess that we could have is not a bad way to think about it. Essentially, this is going to be the we can call this like the way, or maybe better, the best guess that we have. For a specific value of our parameter. And then from the observation that we have here, our best guess for our mean is just what we saw from the sample, right? If we had to pick any random number, we should pick 16.3. But we run into this issue where we don't actually expect mu to perfectly match X bar. In other words, there should be some amount of error. Now, that's not to say that we've made like a mistake. Error in this case is not a mistake. Error in this case is just saying they shouldn't match up perfectly, right? For instance, if we measured every single person and we found out that it was 16.25, does that mean that we did something wrong to get the 16.3? I'd say probably not necessarily, right? Actually, at that point, we'd be pretty happy that we guessed 16.3 because 16.25 seems quite close. And so we have this idea of like, we might see just naturally, just by random luck, a discrepancy between what our guess for the mean is and what the actual mean is, right? That would be our error here. We're a little bit off. And so rather than using a point estimate, what we will often see instead, and this is kind of a good demonstrative that what you are looking at is good statistics. Rather than giving a point estimate, what you'll be given is an interval estimate, or what you would like to give is an interval estimate, which gives a range of possible values for estimating the parameter. So for instance, we do our collection, we take our sample, and we see our point estimate, mu, was 16.3. And we say that's our guess. Versus, maybe we do our point estimate. We say, okay, yes, our best guess is that mu is 16.3, but there's a possibility for error. There's a possibility for discrepancy here. So maybe it's 16.3 plus or minus 0.4. There's a margin of error. Error due to sampling, right? We're just saying, hey, maybe we did our sampling perfectly well, but there might be a difference between what we did for our sample and what we did for our mu. And so I'm not going to say with 100% confidence that my mu is in fact exactly 16.3. I'm going to give myself a little bit of wiggle room. Hey, I expect my mu to fall within a certain range of values. Which of these would we say is more accurate? Which one gives us a more precise guess as to what mu is going to be? So accurate, in this case, we're saying precision. So which of them gives us the narrowest? This is our like most fine-tuned guess for what mu could be. The first one, right? 16.3 is as accurate as we're going to get, right? We're not wavering at all. We're not saying within a certain range, right? We're saying 16.3. That's our largest accuracy. Which answer should we have more confidence in? The second one, right? So the first one has a lot of precision, a lot of accuracy, but we maybe shouldn't necessarily feel all that confident that it's correct. The second one sacrifices some of that accuracy. We're saying, hold on a second, we're actually not sure that it's 16.3. It could be as low as 15.9. It could be as high as 16.4 or 16.7 rather. And we lose accuracy, but losing that accuracy gives us more confidence in our answer. It's a lot more likely that the second one is correct versus the first one being correct. So an interesting observation here would be that we sacrifice precision to gain confidence, right? Assurance that what we are looking at is in fact correct. All right. The 16.3 plus or minus 0.4, that's a perfectly valid way to write it. How I am often going to write this is I would say, well, this is really going to be between 15.9 and 16.7. Notice that I'm saying the same thing here, right? 16.3 plus or minus this value is the same as saying between 15.9 and 16.7, right? It's just a different way to lay out the same information. But I will generally be defaulting to this, the 15.9 to 16.7. But I do want you to be aware that I could represent it either way. right, so questions on our idea of like why we might like want to look at a range instead of like one specific guess. Questions on why we're even constructing intervals, essentially. Well, the good news for us is that the process by which we are going to do this interval construction, we already did for bell work. Again, if you felt really good about what we did on the bell work, this should be a breeze. Or essentially, we're saying, hey, if I want to be really confident in my answer, I want to make sure I have enough kind of wiggle room that a lot of my data is kind of captured between these values. We're going to use some z-scores in order to figure out what this kind of range of values is going to be. In this case, if we are looking for a confidence interval at a particular kind of value here, then the way that we could do this in terms of z-scores, so I'm using ci sub z to indicate that we are doing this in terms of z-scores. We're going to look at how we adjust it, but it's essentially what we did for the bell work of converting from z-score to x value. So not all that crazy. This is going to be, notation here is going to get a little bit hazy, but we're going to pave back over it. It's not going to be too tricky. This is negative z of alpha over 2 to positive z of alpha over 2. Okay, whoa, hold on a minute there. What are we talking about with this alpha over 2 business? Well, we've seen alpha before. Alpha showed up in our review of Unit 1. It was in Unit 1 as well. So it makes sense that it would show up in the review there. If I'm looking at trying to capture 95% of my data, which is going to correspond to 95% confidence ultimately. We're looking at our normal distribution here. We have our z values, we have our z values. We're saying that this stretch here accounts for 95% of the data. Then how much data do I have in this region? 2.5%. And how much data do I have in this region? Also 2.5%. Right. We have 5% left over, right? 5% not trapped between our two values. Half of it is to the left of the leftmost value. Half of it is to the right of the rightmost. This is what we're talking about with the alpha over 2. So recall from our hypothesis testing, alpha was the amount of kind of the likelihood that we fall to those outer ranges. Right, so if we are looking to capture 95% of our data, then our alpha is equal to 0.05. Just to say, there's a 5% chance that we don't fall within that 95% confidence interval that we're trying to construct. We have a 2.5% chance of falling to the left. We have a 2.5% chance of falling to the right. And so that's why we're talking about the alpha over 2. Is the alpha over 2 is essentially just saying 95% gives us 5% of failing, and then we split that in half and, you know, do it across either side. Essentially, though, this is just what the calculator gives. This is what inverse norm gives. Are these z-scores? So it's not particularly crazy here, right? This is literally the 1.96 plus or minus that you guys got from the bell. Okay. Often, though, we aren't going to just leave our confidence interval in terms of z-scores. It'd be nice if that were the case, right? If I'm trying to construct a 95% confidence interval for any particular subject, oh, that's easy. It's going to be between negative 1.96 and 1.96. And as long as I'm using z-scores, then that captures 95% of my data. And that's true. This is always the case. These are always the z-scores that we would use, but we aren't going to be doing that. Generally speaking, we need to convert from a z-score into an x value. Not too crazy. Again, we did that for bell work. So before we said that the z-score was x minus mu over sigma. And so that x was equal to mu plus z times sigma. And that's true. Certainly true. The only adjustments that we have to make are that we are not using the population parameters because we don't know the population parameters necessarily, or really we're not referring to the population parameters when we are taking a sample. So one small adjustment that we need to make, if I'm using the sample mean instead of the population mean, what do I need to change about my formula here for X? Small change, it doesn't numerically change anything that we're doing, but it is worth noting. What's the difference between population parameter and sample statistic if I'm talking about mean? Yeah, we just use X bar instead of mu, right? The values aren't going to change or anything. This is just, we don't know what mu is, and so we have to use X bar instead. Yes, the standard deviation would also change. So what adjustment did we need to make to take our population standard deviation and convert it into a sample standard deviation? Divided by the square root of n. Very good. Very, very good. So the only thing that you guys need to really remember here, the only difference that we're going to find between what we're doing and the bell work is that instead of using the sigma that you're given, if we're talking about a sample, you need to take the standard deviation and divide it by the square root of it. That's like the only difference. And it's what we did in 5.7, right? It's, again, nothing different than what we've seen in Unit 5. It's just because we're talking about a sample here, we do need to remember to do this. All right, let's take a stab at this. We're going to do a couple of these by hand. There are a bunch of calculator functions that I'm going to be throwing at you. And I think the kind of one of the nice things about this is that the math here actually isn't all that crazy to do by hand. And so I want you to feel comfortable with being able to do it by hand. So that if you're in the situation, you're like, I don't remember which of the 6 different calculator options to choose from here, that you are able to figure something out without needing to rely on the technology. I also want you to be able to do it with the calculator, but this one is kind of nice enough that we're going to approach this kind of by hand, and it's not going to be too tricky. We do still need to use the calculator to get the z-scores that we need, so that'll be like the Unit 5 stuff. But then converting from z-score to x value is really the only task that we have. Right. But before we get into that, let's take a look at constructing these confidence intervals just in terms of the z-score, not in terms of the x values just yet. So if we are trying to figure out the z-scores that we would use for a 98% confidence interval, what are we going to enter into our calculator here? So which function are we going to use? Inverse norm, right? Which is the third one. Okay. What is our area here for a 98% confidence interval? 0.98. If I'm looking for z-scores, what are my mu and standard deviation going to be? 0 and 1. And then if I'm looking for between two values, I should use center. All right. What do we get for our interval here? 3, and the positive version as well, positive 2.33. They're nice and symmetric. They're always nice and symmetric. And that's it. How do we interpret what this is telling us? Well, this isn't the interpretation that we're going to stick with, but an interesting thing to note is that 95%, or not 95, right? We're working with 98%. 98% of our data falls between these z-scores. In other words, we have a 98% chance of getting a z-score that lives between them, if we were just picking one randomly. Okay, let's try it with the 93% confidence interval. What do we get for our z-scores here? Well, we don't have a mu or a sigma yet. We'll take a look at those here in a second. Yep. Very good. So again, now the only difference between what we see here and what we're going to be doing is just taking those z-scores and converting them to x values. And the only thing that we need to keep in mind is that because we're going to be working with samples, we need to take the standard deviation and alter it in the way that we alter. All right, let's take a look at our first example here. We're trying to construct a 95% confidence interval for the population mean. Just right off the bat, 95% confidence interval. What are the z-scores that we can attach to 95% confidence interval? Very good. So this is the confidence interval with z-scores. Negative 1.96 to 1.96. Those are the two that we are most commonly going to use, I would say. But certainly I want you to be able to figure out the others as well. All right, so let's go through and figure out our kind of various values here. What is our mean going to be? Or rather, not our population mean, because that's what we're trying to estimate, but our sample mean. 54. In order to find the sample standard deviation, what do I need to do? Yeah, of n, right? Okay. What is our population sigma? I think you're looking at the next one here for just for this first one, for the car one. What's our standard deviation? Population? Yeah, just 6. And then what is the value of n? 50. And so our S, the one that we're going to use is 6 divided by the square root of 50. Is that the 0.58 that we were saying? Or 85? Cool. Cool. Perfect. So this is the mean, and this is the sigma that we want to use. And these are just like stepping stones. We're not really necessarily going to use them for anything. I mean, we'll see that we use them for something like later, but this is fine. Okay, we can now either solve this by hand, which is what, my kind of advice would be, just to start off. But we'll start off by solving this by hand. So this isn't too bad. So in this case, we're looking for the x values that these go with. So in this case, x is equal to our x bar plus or minus that z times s, plus or minus because we're going to be getting one positive value and then one negative value. So this is going to be x being equal to 54 plus, or we'll start with the lower one. We'll do minus first. Minus 1.96 times 6 over the square root of 50, and 54 plus 1.96 times 6 over the square root of 50. We could do the margin of error thing that we saw from this with like the plus or minus 0.4. That's not too difficult to do. So in this case, 1.96 times 6 over the square root of 50. I get 1.663. So our mean here, or our x, should be 54 plus or minus 1.663. Which is a perfectly okay way to represent this. Again, think that 1.663 is like being a little bit above the mean or a little bit below. But as far as confidence intervals go, we're actually going to add and subtract that particular value. So 54, we'll start with minus. So 54 minus this value, 52.34, and 54 plus this value, 55.66. Which is literally just adding and then subtracting that 1.663 from the mean. Okay, so what does it mean? What does it mean that we got a confidence interval at 95% with these values? Our interpretation piece here is that we are 95% sure or percent confident that the true mean falls between these values. It would be too weird, too strange, too unlikely to get a sample like this of this size and not have the true mean fall between those two values. It happens about 5% of the time. Pretty unlikely. Not really. I can do this. That was the z-score that we attributed to the 95% confidence interval. So when you do the, like, just the inverse norm standardized at 95%, those are the two z-values that you get. Which I didn't show us doing it. They were the same ones as the bell work. Yeah. All right. Questions here? How are you feeling? Again, hopefully very reminiscent of what we did in unit 5. Just using inverse norm to get the z-scores and then just converting the z-scores into x values, with the only adjustment being that the standard deviation is sigma divided by the square root of n. Very familiar. All right, take a stab at, we're gonna come back to this one. Take a stab at the 95 and 99% confidence interval. So we already know, what are the z-scores that are attached to 95% confidence? Yeah, that'll be, so this is for the 95% is the plus or minus 1.96, or maybe a better way to write it. And so you'll need to find the ones that go with 99%, but that'll be just inverse norm, figuring that out. And so converting those into the x values that we have, and then doing the same thing for the take units to accept. Right? You don't need to, like, if you can go just from here to here, this is so like, I was writing it. But whatever. This is great. I would save the rounding to the very end, just to make sure that like you don't get it like ever so slightly off. But yeah, this is perfect. And you can on your paper do like 0.91, just like in your calculator, like copy paste this whenever you're doing the calculations. That's great.
You do 2 or 3.
2 is fine. Oxford. I would go out a little bit farther, just so we don't do premature rounding. It works out in this case, but just to be like careful, I would maybe do like if you're gonna round, do like 0.9104 or something, just to be like sure that we're not rounding premature. Or you can copy and paste your answer, like if you go like up here, yeah, there it'll copy and paste it from the first nice. That's perfect. That's right. The perfect, so that's gonna be your lower bound on your interval and that'll be your. Generally the way it's formatted is you'll see it like this. This is also like a fine way to express it. This expresses the same thing as this, but this is normally how you'll see it written out. One of those I would say is like showing the margin of error. It's like our guess with a little bit of margin of error, and the other one is showing like the range of values. But ultimately that should express the same. Okay. So let's take a look here. We can set up the overall. I thought the math looked really good. When we're going through and solving, what are the x values that I get? So it's 26.2 plus or minus what? Did someone calculate this? Seven something. 7. Maybe if you do it without rounding. Or let me double check. Really quick. I get, my goodness, 5.15 divided by the square root of 32. Negative 1.784. Yeah, perfect. Which works it out to give us an interval of what? What's our lowest bound? I think 24.42 to 27.98. Did you get the margin here? It should be plus or minus 1.96 times 5.15 over the square root of 32. We can take a look at it if we need to. Yeah. Okay, what was our okay, and then really quickly, what's our interpretation here? What does this interval tell us? Yeah, 95% confident or sure, whatever, confident that the mu essentially we'll say just lives there. Okay. And then for our 99% confidence, what were our z-scores that are attributed to 99% confidence? Very good. All right, and then what did we get for our x values? 23.85. 28.55, that sounds right. And again, what would our interpretation be? How sure are we? 99% sure that mu lives here. By lives here, I mean like falls between those values. Okay, and at display here, what do we notice about these two intervals? What's going on when we go from 95% confidence to 99% confidence? What do we have to do? What do we notice about when we compare these two confidence intervals?
Bigger.
Yeah, we have a bigger range for which one?
And
For 99%, which tracks with what we observed earlier, right? The idea that I forfeit precision, I forfeit accuracy to gain confidence. So in order to go from 95% sure to 99% sure, I have to accept more values. Right? I have to loosen the restrictions that I have. I have to zoom out a little bit in order to do that. And so what we see here is kind of this interplay, a really actually very important interplay between how confident we are and how accurate and useful our answer is. For instance, I could say that I am 100% confident that BPM is going to live between 0 and 1,000,000. Right? But is that a particularly useful metric? No. So having extremely high confidence does not necessarily mean I have a particularly usable and accurate result. On the other hand, if I say I'm 50% sure that the value falls between this really, really narrow range, that's not a whole lot of confidence in my answer, right? It might be a very exact, extremely precise answer, but I'm not particularly sure that it is in fact reality. And so we get this kind of balancing between what should our alpha be, how much precision do we need, how much accuracy do we care about in order to arrive at this kind of like preset condition of what should our alpha value be. Now, if you want to do really bad statistics, you run the confidence interval first, and then you pick the alpha value that fits the findings that you're trying to support. That's not good. That would be very skeevy. That would not be great. Instead, you try to pick the alpha value to fit your circumstance. Maybe it's not super important that we miss the margin by a little bit. Maybe having 95% confidence for our study is better than 99% confidence for whatever reason. Then we want to run with 95. Or maybe it's really, really, really important that we don't mess up kind of capturing that mu if it is in fact capturable. And so we rely on the 99% confidence instead. It's just whatever the study kind of requires is what you'll fit it to. Not the other way around, right? All right. Questions with calculating confidence intervals? Again, hopefully very, very much just a natural extension of what we were doing in Unit 5. Not too crazy. Okay. Good news for us. I wanted you guys to see this. I wanted you guys to get a little bit of practice doing this by hand because I don't think it's particularly all that crazy to do by hand. We can just get these non-standardized values from our calculator. For instance, if instead of getting z-scores from our inverse norm, I wanted to get just the non-standardized raw scores, what could I enter into my calculator to give me this kind of 95% confidence interval? What would that look like? So if I want to not standardize, if I don't want z-scores, what would I do? So it's still inverse norm. It's still that 0.95. But now, what should we use as mu? 26.2. Okay, what should we use? This one's important. What should we use as sigma? Is it just 5.15? Square root of 32? Perfect. And then do we want this to be left, right, or center? Want this to still be center. And if you enter this into your calculator, you get the exact same thing that we calculated by. You get 24.42 and 27.98. So entirely doable with the calculator as well. There's nothing wrong with doing that. But I didn't want to like flood you guys with a bunch of calculator inputs. That being said, there is another way to do this on the calculator as well. If you go into not second vars, but if you go into stat and you slide over to tests, so stat, slide over to tests, and you're looking at the Z interval for our test. There are two options here. One of the options is actually pretty cool. This will take data and use it to do the computations, which is kind of nice. But in this case, we don't have data. We have the actual like statistics. It's already been calculated for us. So we would use the statistics here. In this case, the sigma that it's asking for is that population sigma. That's just the one that's given. It's going to do the divided by square root of 32 for us. It does that automatically. Our X bar is what we said. We said we wanted a 95% confidence, and we get, lo and behold, the exact same thing that we computed by hand and the exact same thing that inverse norm gives us. So the inverse norm, non-standardized, still works. Exactly like what we were doing in 5.7. That still works. That's still great. We have a new calculator feature that lets us do confidence intervals now, which is also cool. That also works great. Nothing wrong with that. And then calculating it by hand is also not particularly cumbersome. So hopefully 3 different completely viable methodologies to use for confidence intervals. All right, so in your calculators, let's take a stab at doing this one up here. 99% confidence interval for the data that is given. And this time, instead of doing it by hand, try it in your make sure you only hit enter once. When you hit enter the first time, it'll just give you the answer. And then if you hit enter again, it'll give you an error. So for instance, are you doing the inverse norm way? Okay, it's registering you as putting the center there. Yeah, under the thing. So if you go to inverse norm here, this should be correct. Why is it structuring your argument that way?
99% copy.
Inverse norm.
Wait, put a parenthesis on it. In the
Yeah, maybe that's what it is. It's weird that that's creating that issue.
But yeah, you gotta go.
You have to put a
Another
parenthesis.
parentheses at the end of it.
Silly. Okay, so 0.9 is, what? 5.6?
Yeah.
Standard deviation 0.8 divided by the square root of 30. And we're really saying that we need, that's silly. Okay. Okay, yeah, one thing to be careful of that we have just noticed, you need to finish. You need to finish the parenthesis in order to not get an error, it looks like for some reason. Yeah, you have to use your parentheses in order to round out the like square root of 30. Otherwise it gets mixed up. But you can also do the stat test and that should also work fine. So you can either do inverse norm or stat test and either way it should be fine. I don't know why it's being particularly finicky now. Cool. What do we get for our confidence interval here? Just while we're here. What do we get for our X values?
Negative.
So that'll be those are the z-scores. 5.22, I think 2.223 and then 977, something like that, which rounds the way you said. Yeah, I think that's perfect. Yours is great. Yeah, the 2.2 and the 9.8 is also. Oh yeah. You need to change the mu and the standard deviation to be the 5 points. What is it? 5.6 for the, so this would be inverse norm. Yeah, you'd use 0.99. For mu, you would do 5.6. For standard deviation, it's 0.8 divided by the square root of 30. You have to close parentheses on that to make sure it knows that you're done, and then center. That should work. All right, questions with our confidence intervals.
And then it will be the population standard deviation divided by the square root of n.
Assuming we know the population standard deviation, yes, that will always be how we do it. Now, there will be cases that we look at here momentarily, not today, but that we look at later on, where we do not have access to that information, in which case we will need to do what is called a t-test instead of a z-test, or a t-interval rather than a z-interval. And it's slightly different. We have to do some finagling in order to make that work, but we'll cross that bridge when we get there. Yeah, this is specifically if we know the population standard deviation. It's also specifically if we know the population standard deviation and we have a fairly large size of n. Because otherwise, we don't get guaranteed that we're pulling from a normal distribution. But we'll, again, cross that bridge when we get there. You'll notice even the header here is confidence intervals for large samples. And that's using the central limit theorem, which again says if we take enough samples, what we get is a normal distribution. But if we don't take a large number of samples, then we don't know that what we're taking is a normal distribution. All right, one final example to look at, and it's kind of doing the opposite of what we've done kind of up until this point. So let's go ahead. We'll read through the problem here. I think going through and creating an equation for this, they exist, and that's fine. But I think just approaching this problem conceptually is easier than adding another equation to memorize, personally. All right, so we are told that we have a scientist who wants to estimate the average depth of a river. We want to be 99% confident that our estimate is within 2 feet of the true mean. We know that the standard deviation for all of the river depths, this is like the population standard deviation, is 4.38. Okay. We are trying to figure out how large does our sample need to be? What is the minimum sample size that gives us 99% confidence that we are within 2 feet of the mean? Let's start here by, let's just pick a random mean to do this construction. Ultimately, the mean isn't really going to matter for us, which is kind of nice. But if our mean was, we'll just say like 50, what would it mean to be within 2 feet of 50? What would our confidence interval look like if we're within 2 feet of 50? 52 to 48 to 52. In other words, so this is like if mu is equal, or rather if x bar is equal to 50, then our confidence interval should look something like this. In other words, it should be whatever our x bar is minus 2 to whatever our x bar is plus 2. We feel okay with this idea that within 2 feet is the same as being either 2 feet below the mean up to 2 feet above the mean. It's like a width of 4, essentially. Okay. So now we just need to figure out where this plus or minus 2 is kind of coming from. So another way to think about this is actually x bar plus or minus 2. Where did we get this like plus or minus notion? Where did we see this? Where was it coming from? Yeah, that's like the error. So we have our mean, which in this case was 54. And the way we find error is what? What do we have to do to find error? Yeah, so the like sigma over the square root of n, right? And then what do we multiply that by? Whatever the 99% z-score is, whatever that z-score is, that works there. Yeah, brilliant, perfect, super, super good. Right, so this plus or minus 2, this margin of error that we are seeing, should be the same as what we get when we take our z-score that goes alongside the 99% and multiply it by our standard deviation. Now, the standard deviation, as Merrick has done a good job of noting, isn't just sigma, it's that sigma divided by the square root of it. Do we know what n is? No, in fact, we are looking for what n is. And so we'll need to solve ultimately the equation that we get for n. Okay. And the equation that we are solving is the fact that 2 should be equal to z times this sigma over the square root of n. Right? If we wanted to make this generic, this would be that the error is equal to z times whatever, but we know that that error is going to be 2. Right? Okay. What is the sigma that we're working with here? .38. Okay. What is the z-score that goes alongside a 99% confidence interval? 2.58. If I'm going to use +2 as my error, we'll use +2.58 as my z-score. If I were using -2, I could use -2.58 as my z-score. So this is going to be 2.58. And we are solving for n. Okay. There's a whole lot of multiplication going on here. We could start by just multiplying the numerators. That would be totally fine. We could also start by trying to isolate n, trying to get n on its own. What would I need to do to this? Well, actually, we'll do the simplification route first. Let's multiply 2.58. This is, again, algebraically where it maybe gets a little bit tricky. Think of this as 2.58 over 1 times this particular fraction of 4.38 over the square root of n. What do I have to do to multiply fractions? What do I do? To multiply fractions. We don't need same denominator for multiplication. Don't cross multiply. Nope, that's division.
Go straight across.
Yeah, you just go straight across. Numerator, denominator. It's the easy one. Multiplication of fractions is the easy one.
Dividing.
Dividing is the one where you have to do the flipping. All right. So we multiply our numerators together. That's going to be 2.58 times 4.38. 2.58 times 4.38. I get 11.3004. Divided by 1 times the square root of n. Well, that's just the square root of n. Okay. What's my main issue? I'm trying to solve for n here. What's the problem with what we currently have going on right now? Oh, yes, but we're trying to isolate n to get that number.
You have to like multiply.
Yeah.
With
Multiply.
No, we're more than capable of multiplying by a variable. The main issue is it's in the denominator, which we can solve by, absolutely. Yes, we can definitely do this. So we're going to multiply both sides by the square root of n. And then, Liz, what are we going to do to follow up? Divide back out by 2. So this is 2 times the square root of n being equal to 11.3004. And the square root of n being equal to, well, dividing both sides by 2, I get that this is 5.6502. One final step here. What do I do to finally solve for n? Square. To undo the square root, we have to square both sides. I get that n is equal to 31.92. Not packing up yet since we are not done with this problem. 31.92. Is that a possible sample size that we're able to drum up? No. We have to round this to 32. So the minimum sample size needed to have a 99% confidence and be within 2 feet is we need to take at least a sample of 32. Question for you all. If this said 31.4 and we were looking for the minimum possible sample size that fits this criteria, would we round up or down? Is it 31 or is it 32? Mathematically, it rounds to 31. But conceptually, the very first sample size that we could take that fits our criteria is 32. 31 is too small, right? 31 doesn't match having 99% confidence being within 2 feet. We need to take at least 32 before we see that. So even if it was like 31.3 or 31.4, we would still round up. All right. Just a heads up. Quiz on Thursday. Keep an eye out on Schoology tomorrow for the attendance assignment that I will post for you all to complete. Unless you're a junior, in which case you don't need to work. You'll be doing something worse.